Okay, so this is our first lecture after Professor Marco has done the first 2 weeks, and I hope you all enjoyed those lectures. So now let's say the stage is ready for us to go one step further. So PCA, correspondence analysis, basically what we were doing there is to know the structure, the relationship between variables and all those stuff. So you know perfectly those things by now. Now, the next and natural move is to go to regression models. Okay? I hope we are recording. Okay, good. So you already know now the course outline. Everything is on the GitHub page. Okay. So now, going beyond numbers, what this means. Now we have seen in the past 2 weeks and in the introductory course to data analysis about MATLAB, all numbers and those things. Those are pure numbers. Okay. Now the thing is, if you see a random person in the street and you ask him how you look to the world around you, how you look to the traffic around you, how you look to the streets, he would say everything is chaotic. He doesn't see any pattern there. But for us, as a data scientist, as a data analysis, as a statistician, we look to the hidden architecture between the data. So we just don't look it as a chaotic world. We try to extract meaningful information from the data, and based on that, we then relate those information, those structure, those architecture to the real world. Okay? So now, there is a famous saying which says that models versus reality. All models are wrong, but some are useful. What this means? You may sit to make multiple models for a specific task, but as we know, there can be multiple variables influencing our model. Okay? So we can try the best we can. Okay? So this means if we try to change the variables, to change the mathematics of our model, one of the model would best fit for us, and we put the rest to side. So some models are useful and we use them in practice. Okay? So we have to approach it like in a humble way. We say, okay, a model isn't the perfect replica of the world. As an example, for example, if someone say to you, okay, draw me the map of Parma city, okay, and you have A4 size page. What you do? You start drawing. You draw via the Zalio, Department of Economics, Statistics. You go pass by the bridge, maybe to Pilota. Okay? But this is not perfect. Why? Because we miss so many details. So, to replicate the perfect city, we need a page which is as big as Parma city. So, we can have the perfect replica of the city. Same goes for the data. Okay? So, in a sense, we should be humble. Okay? So, it turns out that what we can do is, from any kind of data, we extract the noise, the unwanted information, the information which we don't need for our analysis, for our experiments. We just keep the information which is related to us in the kind of experiment or the kind of model we are intending to do. Okay? So just keep those and extract the rest, what we don't need. So for example, in a regression model, the main idea behind the regression model is to predict the future, to predict what can happen tomorrow, what can happen next week. Okay? So keeping this in mind, we go further deep in detail about every aspect of regression. Okay? Yes. So, motivation. So the objective here for today's lecture is to analyze the dependence between two phenomena, between two quantitative variables. Okay? So we restrict our attention in the case where we have just two quantitative variables for the simplest regression model. Okay? Okay? So the goal here is not to observe the joint variation between two variables. Okay? Let's say we have x and y. We have two variables. X is the input, y is the output. Okay? So we don't want to see just merely how these two moves together. Okay? But our goal is to understand how one variable is dependent on the other, how x is dependent the other way around, how y is dependent on x. Okay? And to know, the second point is, can we predict one variable from the other, and can one variable be explained by the other? Okay, so this is the key idea, the objective of today's lecture. Okay? Now, before going deep, we need to keep some notations in mind. Okay? So for us, y is a dependent variable. Sometimes it is also called response variable. Okay? Which is a kind of output, which is a kind of response. Okay? And x is independent variable, which explain what the phenomena is doing, which is our real data and what we want to investigate. Okay? So for example, for a sample of n statistical units, we observe points x1, y1, x2, y2. As I try to draw something here, let me see. Oops. Okay. You can see clearly the board from every side, right? Okay. So, this is our x, this is our y. We said x is the independent variable. Y is the dependent variable. Okay? So let's say we have a bunch of points here on our scatter plot. Okay? Could be any. So, as we go for the notation, for example, we want to see to this point. So for us, this is x1, okay, and y1. If we want to refer to this point, we would say its coordinates on the Cartesian plane is x1, y1. Similarly for the rest of the points. Okay? And generally we refer to these points as xi, yi, so in a generic sense. Okay? And we go to the end of our data set, which is xn, yn, and n represent the size of your points. Okay? and n is the size of your sample data set. Okay, so these notations should be clear because we will use them over and over and over again. Okay. Okay. Now, as we said before, why we need those subscripts? Okay. For example, xi, yi, x1, y1, x2, y2. Okay. So these are random variables. As we know, a variable is random when we don't know its exact or deterministic value. So here x can take any value, depends on our data. Y can take any value. Okay, so we call the variables x and y as random quantities. Okay, and xi, yi are the realization of those which we will then refer to as x1, y1, x2, y2. Okay, now just sometimes maybe we call to these variables instead of xi, yi, in general, just to make our life easy, x and y. Okay, but if you want to be specific, if you want to be explicit about a point, we then say xi, yi are to the referring to the specific point, x5, y5. Okay, now to really understand now, let's have an example. So in this example, a firm is planning to launch a new mass consumption product. Okay, so we have a firm who wants to launch a new product into the market, and what the firm wants, it wants to calibrate the price for this new product. It wants to know what price should we put on this product so we can have a win-win situation where we can sell more of our products. So in order to know which would be the best price to sell more products. Okay, so they conducted experiment and they decided, let's say, to sell the product in 8 different supermarkets. Each supermarket is in a different province. Okay, so there is no correlation between the supermarkets. One is in Modena, one is in Milan, one is in Bologna. And each supermarket has a different price. Okay, supermarkets are in different places. Supermarkets have different prices. Okay, and sales are recorded per week. Okay, for each supermarket. Clear? So here is our data set. Supermarket A to H, these are different supermarkets. Each supermarket has a different price, and which turns out that each supermarket sells a different number of units. Okay, keeping this in mind. Now, there is a kind of asymmetry between the two variables. Okay, what is that asymmetry? So the two variables plays a very different role, x and y. Okay, so the firm expects that sales are dependent on the price, as usual, as normal for any economic situation. Okay, so the price is already set by the firm. Okay, so it's a fixed value, it's a deterministic value, it's constant value for each supermarket. Okay, and sales are what? Are the dependent variable which responds to the fixed value of the independent variable. Okay, so in this example, for us, y is our sales, and the dependent variable or the explanatory variable is x, which are the prices. Okay, now as you know from the previous course, one can naturally fall to, let's say, let me find the correlation between these two variables, x and y. But keeping in mind, correlation is symmetric. It means that it does not make any difference between the two variables. It treats x and y as the same. Okay? So if you interchange the values of x and y, it will give you the same answer. Okay? Meaning that it gives you just a number. Okay? It does not give you the direction of dependence, or it does not have the capability to answer if you want to make any kind of prediction in the future. Okay? So correlation says to you just, is there a correlation or not? Yes or no? Okay? Now, if you find the correlation of the previous data set, here we find the correlation is minus 0.94. Okay? Which means that there is a strong negative linear association between them, because we have a negative sign, which turns out that higher prices, if we have higher prices, so the sales are low. Okay? This is negative relation. Okay? So as we said, for example, if you want to predict a price at 1.40, okay, which we don't have in our data set, which none of the supermarket has this value, 1.50, and we want to predict this. So correlation cannot help here. Okay? So, because of this reason, we go to regression. Okay? And we explained this before, xi dependent, y is on the vertical, and the horizontal axis is xi. Now, even in the regression model, for example, if you have on the x-axis, let's say you have study time, okay, and on the y-axis you have grades. Okay, so for example, if both of these variables, the grades and the study time, if they both increases, let's say the study time goes this way, so it's natural that the grades will go this way. Okay, so you are studying more hard, you are giving more time to study, you will have then a positive relation, right? But instead, if we, in place of this, we put social media time. If you are giving more time to social media, what happens? This is increasing, but this is decreasing. So then we have a negative relation. Okay? So similarly, in the pattern of our data set from the supermarkets, if we see before doing any kind of models, before doing any kind of mathematics, if we closely look to our data, what you see? Is there a positive relation? Is there a negative relation? Any guess? Yes, we have a negative relation, because as the price moves up, the number of sales decreases. Okay? For example, at 1.45, we have 450 units sold. Okay? But if we move up to 1.50, we have a decrease in the number of items sold. Okay? So these points suggest that there is approximately a linearly decreasing relationship between the price and the sales. Okay? Now, so higher prices is discouraging demand. Low price stimulates the number of sales. With low price, we sell more products. Okay? So now, To choose the model, we have to look to two things: theory and empirical observations. Okay? So based on the theory, we saw the data, we have a negative linearly relationship. Okay? And what we do then to choose and approximate this kind of relationship by a linear function. Okay? So before, what we were doing, we just saw the data and we deduced that, okay, there is a decreasing relationship. But we cannot do this for any kind of data. Okay, now we have few rows. 8 supermarket, 8 rows. Maybe we have a data set which has 10,000 rows. Then we cannot do this kind of a quick relation. So we need a function. Okay? And that function should be capable to summarize these relationships. Okay? To summarize the behavior of yi, the dependent variable, is a function of xi. Okay? So this makes our life easier. Okay? We then don't need to look at each row of those 10,000 rows of data set. We just put them in the function and we see if there is a relation, what kind of relation, and then we can do some kind of prediction. Okay? So, as we say here, it's difficult to communicate succinctly what's going on if we have a big data set, and it's unsuitable for prediction. We cannot do this from the back of our head. Okay? And is then insufficient for formal scientific verification. So for these reasons, we need what? A function. Okay? And the function is what? What would be the role of this function? To make the relationship between x and y. Okay? And this is an analytic function. We choose this function to be as close as possible to our data. Okay? So informally one can say we need a function which should pass through all the data. Yes, exactly. Or adopt to our data set. So we can have maybe something like this or something like this. Okay? But we need a function that fits the data really well. Okay? So this is the objective of this function. Okay? Now, in general, it is not mandatory and it is even not necessary and it is even not a good practice that this function should pass exactly at each point in our data set. Okay? So, the goal is not a perfect interpolation that we should pass by each point. Otherwise, it would be a perfect world. Okay? But the goal is to approximate. Because our goal is what? To summarize our data. So for summarization, we need the best approximation, not a perfect interpolation. Okay? As close as possible. So we use these mathematical criterion for those. Okay? When we have this function, and we have this discrete set of observation, we replace it by a continuous functional relationship with the help of this function. Okay? By now we know this is the structure of our data set and we know the dependent variable y to be a function of x. Okay? Where y is the realization of the data x we have. Okay? So, till now where we are? We need a function and that function should do some fundamental purposes. The first one is to summarize our data, to do prediction, and to make some scientific verification based on those summarization and based on those predictions. Right? We are all here? All clear? Any confusion? Okay. So now we need this function, okay, and we use this for prediction, okay. How we can use this for prediction? Before we were saying when we had a correlation, if we have a new price, let's say the supermarket has fixed those prices in advance, but tomorrow they want to know, okay, now we have this data set, but we want to check a new price which was not included as a price mark for in the previous ad supermarket. So they say, okay, now we have a new price 1.40 and we want to test the model to see how many items, products we would sell, okay. So this function can help us to do this kind of prediction, okay. So this was impossible by alone using correlation, okay. Now in statistical interpretation, we can use some economics. For example, a change in a percentage of interest rate, what will happen, okay, maybe some in physics, in biology, to see the genes, if this gene has changed, if we have a new kind of, let's make some prediction, okay, in social sciences to see human behavior, okay. For example, if we have a data set for someone who is eating 3 times a day, okay, and we have monthly data for each day, and then suddenly we say, okay, he consumes this much calories every day. Now we say, okay, if this guy eats just 2 times, twice per day, how much calories he will consume, okay. Or in other scenario, we want to see after 3 months, looking into the pattern, looking into the data set, and let's predict how much calories on that specific day he will consume, okay. Now we know we have the data which is xi, yi, okay, in a form of a point cloud. So we have this cloud random data, we call them xi. We need this function, and now we know why we need this function, okay. Now we know the objective of this function. So for the simplest linear regression line, the regression model goes as follows: yi hat equal to a plus b xi, okay, which is equation for a line. So yi hat here is what? Is the output, the dependent variable, okay. A is what? The intercept, okay. B is the slope, and xi is our data, okay. So let's say we have a point cloud of data, okay. We have this regression line, okay, and then later we will see how we need to best fit it into the point. But just to make this point clear, this is our A, okay, the intercept with the vertical axis, with the y, okay, we call this A for now. B is the slope of this line, which means that how much change we have in x, so how much we will observe on the vertical axis for the dependent variable. So this is the slope, okay, this is our intercept, okay, clear? And this is the regression line. You will see this more in detail, but just to have a big picture for now, okay. Now the key question here is these parameters A and B, how to choose them optimally. By optimally we means how to reduce the error between the observed points and our regression line, okay. So, just to start from the beginning, okay? To have a visual in your mind now. We have a data set, we have a point cloud, we have points, okay? So our points are, let's say, here, 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 okay? What we want now, a function to do what? Summarize this data set, okay? So the equation is there. We draw a regression line based on this equation, okay? And our goal now is, because if you see, in the beginning we said, we cannot replicate it perfectly. This line should not go like, I don't know. Yes, then this is something else, okay? Yeah. So, okay, we have this line, but the problem is, we are missing most of the points, above and below, okay? So the goal is now, these are xi, yi points, okay? This is what we have predicted. This is yi hat, okay? Now, our goal is to minimize this vertical distance between the observed point and the predicted point, okay? It's clear. So how we choose these 2 points, which is the next target, A and B, how we can choose them, so we can minimize this error between the predicted line and the observed data, okay? Now, to optimally find these points, we must define a fitting criteria, okay? And what is the fitting criteria? We need to know the observed values minus the predicted value, okay? This difference is called residual, okay? The observed point minus the predicted point. This is error. We refer to it as a residual, okay? And now, putting back the values of y hat, okay? So we have this error is equal to yi. Yi is what? The observed value, minus yi hat is the predicted value. So yi minus, we have equation for this, okay? Let's put this equation here again, okay? So this is the way to know how much error we have at each observed and predicted point, okay? Now to choose the best value, the optimal value of A and B, we use least square fitting criteria, okay? We call it least square principle or least square fitting criteria. It goes like this, choosing A and B so that we minimize the sum of the squares of the residuals, okay? So here for each point we have a residual, for each point we have an error. We take all those points, we square each of those residual, we sum them, and then finally we try to minimize it. So we come as much close as to the fitting line, to the regression line, okay? Now, why we have squared here? Yeah, this is one of the reasons we want our results to be positive. The other reason is, for example, maybe we have an outlier, you can say, are further above a point like here, okay, and which maybe is because of an error. And if we include this point in our data set, we can make a big blunder. Yeah? So what we do to square it, we will get a big number. So we can recognize, okay, here is something not really correct. Okay? So we penalize it by a large deviations. Okay? So the first thing was to ensure non-negativity. We take all of them as a positive numbers, and to penalize if we have large deviation. Okay? And this gives us a smooth differentiable objective function. Okay? Now, the least square problem is equivalent to minimizing these two functions of a and b, because we are interested to know now how to optimally choose a and b. Okay? So, if we solve these equations, we reach to this result for b. Okay? Now, we try to prove it, right? You ready? Okay. Problem is the other device is not working for me, so we do it here. Okay? So what we want to find, the best values for B and the best value for A. Okay? So once we know the best value for A and the best value for B, then we minimize those residuals and we have a good result. Okay? Tell me if you can see the board clearly. Okay? So, from where we start? We have this equation. Okay? Yi is equal to A. Is there something not going good or what? Any confusion? Okay. So we have this equation, okay, for the line. Clear? Okay. And here we want to know what is the best A and what is the best B. Okay? So, and then we said this is a function of what? Of A and B. And by the least square criterion, we said we should sum all those numbers, which are yi minus y hat and we square them. Okay? Okay? Then what we have here is the error term. Okay? So the error term was what? Y minus A minus bxi. Okay? You following? Okay. Now putting here the value of y hat. Okay? It becomes summation from I to n yi minus A minus bxi. Okay? So this is our equation number 2. Now, to obtain the value of A and B, we should perform differential equations. Okay? So for the first part, let's derive it with respect to A. Okay? So summation from I from 1 up to n. We differentiate this. Remember by chain rule. Okay? What we have here now is 2 times yi minus A minus bxi and we have 1 because we are differentiating it with respect to A. Okay, this is just simple chain rule. Okay? Yes. So by chain rule, this goes down and we are doing it with respect to minus 1. Okay. So this is our, this goes equal to, now take the constant out. Okay? Minus 2, summation from 1 to n, we have yi minus a minus b xi. Let's call this equation number 3. Okay? Now, taking this equation and equating it to 0. Okay? You cannot see below, right? Okay, something very big. We'll try here. Otherwise, you will not be able to follow. Okay, here I have it. Okay, let's try here. Maybe you can follow here better. Right? Okay, so what we want to do here is to know the value of A and B, and our mean criterion is a function of A and B. Okay, replacing yi hat with its value. Okay, we have this. Now let's do first order differentiation with respect to A. Okay, we take this. Okay, we differentiate it with respect to A. By chain rule we get this. Okay, now take out the constant, so we have minus 1 and 2. Minus 2, we have this now. Okay, now putting this equation equal to 0. Okay, when we put it to 0, minus 2 goes out of the window. Now expanding this summation. Okay, we apply summation to each term now. Okay, so summation to yi, summation to a, but a is a constant term which is an intercept, so n times a. Okay, minus b is a constant, take it out from the summation, we have left here just xi equal to 0. Okay, now we know the mean. The mean for anything is what? Summation of all the variables, sum them, divide by the total number. Okay, so which we represent by x bar for this and y bar for this. Okay, are we good? Okay, so what we have now, this, divide this by n, so we will get y bar minus a, divide this, when we divide this by n, so n and n cancel out, when we divide this by n, we have x bar equal to 0. Okay, now solve it for a, so a, rearrange it, a equal to y bar minus xi, b xi. Okay, okay, the same goes for b. Okay, take the same equation, derive it with respect to b. Okay, with the same chain rule. You have 2, here you will have minus xi. Okay, We are taking this equation, now we are deriving it, we taking the differential with respect to b, as we did before for a. Okay, we have this, take out again the constant out, we have minus 2, let's equate it equal to 0. Okay, clear? Okay, now taking these two equations, this for a, so a is equal to y bar minus bx bar, and this equation number 9. Okay, we substitute here the value of a. Okay, putting just here the value of a equal to 0. Now expanded. Okay, what we have, y bar yi minus y bar minus and minus plus bx bar minus bx. Okay, clear? Equal to, now rearrange these terms. Okay, we have yi minus y bar minus, take b common from here, so we have minus b xi minus x bar. Clear? Okay, now let's rearrange it again. What we can do here is yi minus y bar from this side, okay, and minus b here. Okay, what we did here in the previous step is we just expand the terms inside the brackets. Okay, and we got this. Okay, now what we are doing is putting this in place of this in this equation. So what we have, xi times yi minus y bar minus b xi minus x bar. Okay, and equal to 0. Now apply summation to all terms. Okay, so the first term is this, multiply xi with this first term, and we apply summation. Then to minus b, which is a constant, apply summation to this term equal to 0. Okay, now remember this key identity. We have y bar minus y bar, or in the second case xi minus x bar. Both of these things are equal to 0. Why? Because we have the regression line, so we have some positive errors, we have some negative errors. So if we sum the positive and the negative error, it gives us 0. Okay, so this is because of that. Now we take an identity, and this identity is equal to xi yi minus y bar equal to this term. Okay, how is it? Let's prove it. So we say this term is equal to this. Okay, so now let's take the right hand side, which is equal to, okay, and we do the simple multiplication here. Okay, inside the summation and split the summation. Okay, so x bar multiplied with this term minus xi multiplied with this term minus x bar multiplied again with this term. Okay, and we apply summation to both terms. Clear? Okay, now what we have here is this minus this x bar, and this term is equal to 0. Why? Because we say here yi minus y bar equal to 0. Clear? Okay, so this is 0. This term goes off. So we prove that this right hand side is equal to this. Okay? Clear? The same goes for the identity, the next one. Okay? Now we prove these two identities. Now what we do is to take our equations, okay, this equation we left here, right? Okay, and in place of this we put this value. This is what we proved, right? So in place of this value here, we put what? This, right? This is what we just proved, correct? And in place of this we put the second identity, which is this, right? Okay. What we did is just we substituted both values, okay? And then by rearranging this, okay, we have b, take this to the other side of the equality, we have b, summation this, then divide both sides by this summation. So b is equal to this term divided by this term, okay? Clear? Shall I repeat or good? Okay. So we got this value. It can also be written in another way. If you are interested, we can also do the proof, okay? Which is more or less the same way you take those two values and you differentiate them, and then you, okay? So after the class, if someone is interested, we can also derive that, okay? Okay, so now we have the value for b, and this is the best value we can get, okay? Similarly, okay, we did all this now, and for a we have this formula. So what we wanted to do is to find the best optimal values for a and b. We can get those optimal values of a and b by these two equations, okay? So this equation will give us the value of b, the optimal value of b. This equation will give us the value, optimal value of a, okay? Now, if you put the data we have for the 8 supermarkets into these two equations, for a we will get this value 1064.032, and for b we get this value, okay? Then we put those values in place of a and b in our fitted line equation, okay? Clear? Okay. Now, a key point here is, yes, we are now going to, yes, we will now, this is the next step. But before this, okay, what we have, for example, in this case, if we have the value of a x equal to 0, so this means for our data, the value of x was what? X was what? The price. So if price is 0, we get this much intercept. So this means we will sell this much products at 0 price, okay? Which is completely not a better idea to sell everything for free, okay? So the idea here is for this intercept, sometimes it does not have a meaningful answer, but it just helps us to start the regression line, and we have to start the regression line from somewhere. Yes, just a geometrical interpretation, and which is in this case at least from where to start from here, or to start from here, or to start from here. Okay, so at value x is equal to, its meaning is just to indicate us from where we start our intercept. Okay, now, and the meaning of the slope here is, how much change we get on X, so the corresponding Y is changing. Okay, so for example, in this example we had, as what you were saying before, B is minus 422. So its interpretation is, if we have an increase of €1 in price, what it does, it leads to a decrease in 4 to 3 units in sale. Okay, so this is the basic meaning of the slope. We change the slope by what? By €1, and we get a decrease in units of about 423 units. Okay, now we are clear about the meaning of A and the meaning of B. Okay, so now even in if you want to rescale our units, for example, we want a much lower unit. So instead of using euro, we say let me check if we change the unit from euro to cents. Okay, so for example, at 0.0 or at 1 cent, what it would be, if there is an increase of 1 cent in price, what will happen? The sale will decrease by 4.23 units. Okay? Now, so far what we did is we described the sales as a deterministic function of price. What we said, price was already chosen by the firm. Okay? And sales was what? Was the observed values of those fixed prices. Okay? So this means that even when the price is fixed, we cannot determine the sales uniquely. Okay? Why this? We will see. For example, if we note our data set, yeah. So what we mean by that, if we have a fixed price, but we observe different thing. Why? If you see, for example, in the case when the price is 150 in different supermarkets, and also here we have the price which is fixed. So the prices are the same. Okay? Here and here the prices are the same. But if you see, the products sold are different. So we have 440 and 420. Okay? So this means that even fixing the price, we cannot uniquely determine the value of the dependent variable exactly uniquely. Okay? Where we were. Okay, so this means there is some variability, because two supermarkets in different provinces, they have the same price, but the number of items sold are different. This means there is something else to the model. Okay, so to what we can now attribute this variability, this difference between the two supermarkets? Okay, even they have the same fixed price. Okay, so beyond the price, what we have, there are also other additional factors that enters our model, and those are, for example, in this example, per capita income of X province is different than X2 province. Okay, maybe the population size of one province is different than the other. The local preference, maybe someone want to go to this supermarket, maybe the other want to go to another supermarket. And there is also competition between supermarkets, how they put their products on the shelf. So there are many other variables which comes into the picture. Okay, and this then by extension we cannot include all those variables into linear regression. We then go for multiple regression. Okay, but for now our focus is just to study each and everything about linear regression. Okay, so now let's make another experiment. We say we want to do a control experiment, and in this experiment we suppose all the provinces have approximately the same income. Let's say their income is the same, their population size is the same, and the firm set the exact price for these two supermarkets in different provinces. Okay, now what do you think? Can we expect the same sales value to be observed again? No, absolutely no. Okay, why? Because repeating the same experiment will have a different results. Why? Because
there are multiple variables.
yeah, yes. For example, let's say we do experiment on day 1 and we see is rain. So not so many people are coming. Okay? So for each time when we have a different experiment, we have different outcomes. Okay? And these differences cannot be predicted in advance. Okay?
But basically the results are not that big different. There is not.
Yeah, but still there is difference
Yeah.
in this small experiment. But let's say,
have like an approximation value.
yeah, but for example, in the 1 cent example, if we increase the price by 1 cent, we have a decrease in 4.23 units. If we increase it by 5 cents, we have 20 items of decrease, which is a very small change from 1 cent to 5 cents. Correct? This was your question, or I understood you correct?
Yeah.
Okay. So even after accounting for these kind of factors, some variable still remains. Okay, so there are still some variables. Okay, and those variables are because of two reasons. Some are partially because of the price, and some are the factors of nature which we don't know in advance. Okay, so sales cannot be determined with ultimate certainty, and there must be, therefore we have some random stochastic variable. We have to treat it as a random variable because each time we have a different outcome. Okay, so this means we have a stochastic process here. Okay, yes, you're confused about stochastic.
Yeah.
Okay, you mean what we mean by stochastic? Okay, it's a random process which you don't know the perfect outcome, the deterministic outcome. So each time you do the experiment, you get a different outcome. Okay? So now the nature of these control variables. So the price was what? Was set by the firm. Okay? They do not arise from the experiment. So we have already this fixed price. Okay? And so we don't treat the price as a random variable. Okay? Clear? So, but the outcome we have is a random variable. Okay? The sales are the outcomes of those experiments we did. Okay? Because in each different supermarket we have a different condition. Okay? So that's why we treat sales as a random variable. Okay? Now, So each time, as we said before, each time the firm records the amount of sale in a province, it performs a random experiment. And the assumption here is, if the experiments carried out in different provinces, they are different, they do not influence each other, so the outcome from each province and the outcome between them, they are independent. So there is no correlation between those supermarkets. Okay? Just a slide for change for the notation. The lowercase letters we were using is it for the observed realization. Okay? What we have xi and what we observe is a yi. And uppercase yi we refer it to as an experiment. Okay? So y1, y2 and capital Y8. These are independent random experiments. Okay? Now, earlier our experiment was, our interpretation was, we treated y as a generic dependent variable. Okay? We said it depends on y, on x. Okay? On the observed values. But now the current interpretation is, for each experiment, capital Y, we said it's a random variable which denotes our sales. Okay? And yi is the realization of each experiment. So we have a big experiment, capital yi, and inside this experiment, what we do every day for the whole week, we refer to each of those outcomes by small yi. Okay? So this means now we are moving from the descriptive viewpoint to a probabilistic one. Okay? Which means that for each value of xi in this big experiment, okay, we have a different outcome. So yi, each experiment, the output of the dependent experiment depends on x. Okay? X is the whole set of experiments, and inside now to which experiment or to which day we are referring or to which points we are referring, we say to it, we denote it by small xi. Okay? And this is then a probability distribution. Okay? So this means that there is not a single deterministic value for the sale of a given price. Okay? So for a given price, we don't have a deterministic value. Okay? It can take any possible value. Okay? So if it takes any possible value, it has a distribution. Okay? Clear?
So we can find the probability of having a determinate quantity for every x for every level of price.
For every level of price, and then inside that we cannot say to it, okay, let's say for this price, this value, we have a deterministic output, as we said before. So every experiment is a random, and we can have, based on the probability, we can have different outcome. So we then treat it as a probabilistic outcome.
So we can also do like a confidence interval.
Yes, that's where we are setting the stage for. And these things we will use then to construct the confidence interval, the p-value, and the prediction. Okay? So now, the first assumption for this kind of linear models is, if those random variables and those random experiments are independent, so each supermarket in a different province is independent from another supermarket, so they are independent, okay? They are independent random variables. So we take this assumption. Okay, this is our first assumption. The experiments are independent. Okay, keep this in mind. Okay, now, okay, we said this. Let's recall our model. The simpler linear regression model, we can write it in this form. Before, we wrote it in yi equal to a plus bxi. Remember? Yeah. Now we have a change of notation. In place of a, we write alpha, which is the standard notations. In place of b, we write beta. Okay? And then we have a new term, which is plus epsilon I. Okay? So by now we should know yi is the random variable, which is the dependent variable. Xi is the observed value, the explanatory values in our model. Okay? Epsilon is the random disturbance now. This is the new term. Okay? So these are the values which we don't know, which we cannot get from the data. So we have the data, but we cannot find this random disturbance. We saw before they are related to nature. Okay? Alpha is the intercept, beta is the slope parameter here. Okay? Equivalently, this model, we can write it as follows. We take the expectation of the dependent variable such that x, which is the observed value. So we take the expectation of this and we get the smooth line, okay, which is basically the same for this. Okay, clear? Okay, so for each x, the dependent y has a distribution, and if we take the average value of this distribution, we get a straight line. Okay, now why we have a condition here? So the idea here is the explanatory variable x does not determine a single outcome. We know now this is not a deterministic. Instead, it determines a distribution of possible value. Okay, so before this we were dealing it as a deterministic model. We said we have a function which gives us a value depending on x. But now we are in the stochastic model. We say why the outcome, the dependent variable, is such that it depends on a random x. Okay, and that's why we take the expectation. Okay, clear? Okay, now for the linear function we have a bunch of assumptions which should hold for every linear model. Okay, so the first assumption is for each statistical unit I, this equation which we have is should be linear. Okay, so we should have a straight line. Okay, we cannot do some kind of zigzag. Okay, it should be a straight line. This is the first assumption, and this is basically for alpha and beta. So alpha and beta should be in such a way that it gives us a straight line. Okay, now assumption number 2, the mean of the error, the new term which we have now in our model, this one. Okay, this is the error term, so its mean should be equal to 0. Okay, so if we take its expectation equal to 0, how to prove it? We have our model. Okay, we take expectation while keeping xi as a fixed value in this case. So what we do, take the expectation, okay, and we say the expectation of this, if this is equal to 0, if this expectation, this is what? Again the error terms, and again some of the errors will be above the line, some of the errors will be below the line, and the summation of those will be equal to 0. Okay, so if those errors are equal to 0, we get this line. Okay, clear? So basically we exclude this kind of natural errors from our model. Okay, the third assumption sorry, is called homoscedasticity. It's a difficult word. Okay, it says the variance of the error term should be greater than 0. Okay, what this means, the variance of this is equal to sigma square, and this should be greater than 0. Why? Because the spread of the outcome around the regression line is the same for every xi. Okay, this means, as we said before, when we square the model, if we have a very far point, a very far error, it's a problem. Okay, so we say the variance is more or less should be greater than 0. Okay, so there must be some kind of variability. Otherwise, if you have a same value, it doesn't make sense. Okay, and it should not fan out. I mean, the points, the observed points should not be too far away from the fitted line, and it should not be too much fan into the line. Okay, otherwise, in the first case, is not good. In the second case, you are going to a perfect condition. Okay, so we need some randomness. Okay, if this value is equal to 0, the outcome would what? Would lie exactly on the regression line. So this means we don't have any randomness, and this contradicts our motivation for prediction and for regression. Now, the next assumption is there must be no correlation between this error term. Okay, so the correlation between one residual and another residual should be 0. Otherwise, then they are following some kind of pattern, and there is some kind of autocorrelation. This means that one outcome or one observed value is imposing something on the other observed value. So across the error term, the correlation, the covariance correlation is equal to 0. Okay, so there must not be a systematic shift move within these error terms. Okay, so okay, assumption number 5. Okay, there must be no relation between error and the regressor. Okay, regressor is xi, the observed values, the explanatory variables. Okay, if between the error terms and the observed value, if there is some relationship, this means that the data is influencing those random errors. Okay, so this must be equal to 0. Okay, if this is greater than 0, then we have some kind of effect. Okay, and this must be omitted. Assumption number 6. If the disturbance term can be regarded as the sum of many small effects, some are positive, some are negative, at the end it turns out that they follows a normal distribution. So the error for one variable, the error for the next, the error for the next, the error for the next, it kind of follows a normal distribution if you sum all of these error terms. Okay, so many small errors combined makes a normal distribution, a Gaussian distribution. Okay, now implication of it is if the errors are jointly Gaussian, this means that they are uncorrelated. these errors. If they are uncorrelated, this means that the errors are independent. So what we were saying before is correct. Okay? And we can relate these this assumption to the previous assumptions. Okay? Now, normality here is crucial. Okay? And we will see this when we are going hypothesis tests and for the confidence intervals, for the t-values. This normality will play a key role. Okay? Now, the descriptive approach and the inferential or stochastic approach. Before we say that we had this line, okay? Everything here is deterministic. Okay, but now we wrote it just like this. So what's changed from descriptive to inferential is we just change the symbols. Okay? Okay. Now the least square criterion, we had this, right? Okay. And we should minimize this value to get alpha hat and beta hat. Okay, which we said before is A and B. Okay. Now and then we saw this derivation before. Okay, clear? And we see the means x bar here is what the sample mean here. Okay, sum of all the values divided by the total number. Okay, so beta can be found by this equation, alpha can be found by this equation. Okay, putting here the value of beta. Okay. Okay, now to prove this. Okay, how to get beta hat. Okay, let's start from the numerator. Okay, numerator is xi, this value. Okay, let's multiply those terms. So multiplying this with this, multiplying this with this, we get this. Okay, and therefore apply now the summation. Okay, what we get here, if we expand this, we have this term, we have this term, and y bar here is a constant value, which is basically the sum, so we get the constant value. It does not depend on I. Okay, so this goes off. Okay, we take here, we have this value. Now we know before we saw that this term is equal to 0. Okay, because positive, negative, above, below the regression line is equal to 0. If we put this into the equation, this term equal to 0, we have this now. Okay, and this then proves that our numerator becomes like this. Okay, and this step we achieved by putting this equal to 0. So we use just this assumption. Okay, so beta hat can be found by this value, and which is what? The weighted sum of the observed values, the responses of yi in terms of x and yx. So the total, the sum of the spread of those values. Okay. So what we did here is we removed the intercept a kind of. So this formula, this equation can give us what? Just the understanding of beta, how much beta is contributing into our linear model. Okay, how much the slope affects the model. Okay, now till now what we did, we have no explicit assumptions about the distribution of the explanatory variable x. Okay, what we said is, before we were just focusing on the model yi, what is our output? Okay, given that the observed value is xi. Okay, but what about xi? Is xi a random variable? Is it a fixed value? Till now we said the film fixed this value. We said it's a constant value. Okay? And why this matters? Because the meaning of our regression changes if we take this x value as fixed or if we choose this value to be random. Okay? So here comes our assumption number 7, non-stochastic regressor. It means that it is natural to have this value of xi fixed a priori. Okay? So we fix this value, we treat it as a constant. Okay? So whatever, who is doing the experiment says this value is constant. Okay? As we see in our example, the price was fixed. Okay? So this is the constant term. And the randomness only enters because of the epsilon, the natural errors, which we don't know from the data. Okay? We can just find the residuals, but the rest of errors we don't know, which comes from the outside space. So that is the random part. Okay? Now, if the value of x is fixed, what we say, we analyze the variability of y, the output of our experiment, given that the observed value is xi. Okay? And then if the value is fixed, so this means its variance and expectation is constant. Okay? But the other way around, if x is random, okay, if our observed value is random, for example, in the supermarket example, in one supermarket we have 1.40 for day 1, okay, and the next day they change the price to 1.45, okay. So now we don't have a fixed value for the whole week. Each time we have a different value, so now it takes a random value. Okay, if this is the case, then what we have? This is our equation. Now x is taking each time a different value. Okay? Clear? Day 1, day 2, we have a different value, a random value. Okay, so the expectation of y such that capital X, the experiment takes a random value, and this is equal to this now. Okay? So, if we have this case, the randomness case, then everything depends on this value of x. Okay? So the linearity then depends on the new value each time it takes. Okay? And then this has a distribution whose mean is this. Okay? Now this value, beta x, this is this value which is kind of changing each time, and we have a random value. Okay? So the slope now depends on this value of x. Okay? Clear? Okay. As we said, in most common practices, this value of x is chosen to be fixed in most of the social sciences and in other experiments. Okay? And why we take it fixed? We take it fixed because just to know the output of y.
If we have x that is random, we have multiple lines.
Yes, because each time then we have a different, completely different observed values, and the slope will change. So in a sense, if we have a fixed value, we have a fixed intercept, okay, and we have a fixed slope, okay. Then each time we make a change in x values, The slope is fixed, it does not change, but each time the value of x changes, we just multiply the same constant slope by the value of x. But the other way around, each time you have a different slope. Okay? Okay. It should be considered every time when. Okay, sorry. Now, we have another term which is called identifiability. Okay? Which is a practical requirement. What is it? Beyond those assumptions about randomness, we should take care of this. Now we will see what it is, but without this identifiability, the slope cannot have a meaningful answer. Okay? And the regression model will not give us a meaningful information. Okay? Now what is this condition? It is V requires this value, which is in the denominator for our beta, x minus x bar square. This must be strictly positive. Okay? The square value of these terms must be strictly positive and finite. So greater than 0 and less than infinity. Okay? Why is that? If all the values, let's say x bar, the mean values are equal to x, then this means that the difference between them is equal to 0. Okay? If this is equal to 0, this means that there is no variability. Okay? So everything is on the mean line. Okay? If there is no variability, this means there is no slope. Okay? And then we cannot use the equation of the linear model. Okay? So this must be strictly positive. Okay? Again, if it's equal to 0, this means that the observed value x1 is equal to x2, x2 is equal to x3. Okay? So we would have a condition like this. We would have a condition like this. If all the values of x, just take x1 is equal to x2 is equal to x3 and so on. We will get the points here, here, here and here. Okay? Because all those values are the same. Okay? So this means we don't have a slope here. We have just a vertical line, and then we can multiply our linear model. Right? So that's why this should be strictly positive. Okay? Now, let's revisit our assumptions. Okay, we had 3 assumptions in the beginning. The first one was 0 mean, then we have a constant variance, and then we have a lack of correlation. Okay, to clarify what actually this means, we have seen this, so now we should know just a kind of reminder. Okay, so the expectation of this should be equal to 0. We have some positive, some negative, so there should be not a systematic dominance. Okay? Okay, which is the same thing for all the others. Then we have a variance, but the important thing here is when we have this assumption, okay, homoscedasticity. Okay, sometimes it is not reasonable. Why? Because consider a scenario where we have a firm and what they want to do. to model the profit as a function of turnover. Okay? So for example, we have two different firms. Okay? One has initial profit, let's say 2,000 euros, and the other one has, let's say, 5 million of profit. Okay? So the first one has 2,000 euro profit, the second one has 5 million. And after 1 year, the turnover gives more profit, and it is like the 2,000 become 4,000 and the 5 million become 10 million. Okay? So there is some variability, we can see. Okay? The profit becomes double, but the problem here is the variability in the first is small, 2,000 to 4,000, but in the next from 5 million to 10 million. Okay, so there is a big shift. If you want to model these two together, we will have a very big difference of units. Okay, so because of this reason, sometimes this assumption is not reasonable. Okay, so the variability is there and it should be different. Okay. Now, the other assumption was the covariance between the error terms should be equal to 0. Okay. But in practice, also sometimes this covariance in many scenarios is not equal to 0. Okay. So it violates. Why? Because sometimes a positive error is likely to followed by another positive error. Okay. So you can sparsely find a kind of pattern here. Okay, and this is more common in time series or longitudinal data sets. Okay, when you have a time series of data, maybe there is a sudden crash in the market. Okay, it follows this, so maybe next week we can expect another crash. Okay, crash is what? Is external effect. Okay, so sometimes this covariance or correlation is not equal to 0. Okay, and this we know is by. Okay, now we had two kinds of errors. The first error was this disturbance term is a random variable, and that is not directly observed from the data. Okay, so we cannot observe this from our data, which we know by now. We cannot measure it. And the other observable error we have is the residuals. So we have two kinds of errors. Okay, one is the disturbance term, which we don't have a way to measure it. The next one is the observable, which we can find with the help of residuals. Okay, observed values minus the predicted values. Okay, so just the distinction between the two errors, two kind of errors. Okay, now the thing here is now to why we need a good fit for this line, for this regression line. Okay, once we estimate our regression line, we must see now how good this line has fit our data. Are we satisfied? Are we not satisfied? Is this line is a good one? Is not a good one? Okay, how much variability it captured in this line. Okay, because we can have multiple lines can pass here. Okay, so we have our data. Okay, now we don't know which one is the best one. This one, this one, this one, this one, or this one, or this one. Okay? We define the criteria, the least square criteria. What we do there is to find the best values of A, the best values of B, alpha, beta, to minimize this error and find the best line. But are we satisfied? The value of A chosen, the value of B we chosen, these are good values? How we can self-evaluate and say the line, the values of alpha, the values of beta, the way we chosen gives us a best fit. Okay? To know this, we have these three quantities. Okay? So this regression line that includes this intercept, one can show it fundamentally a decomposition of these three things. Okay? Okay, so though we have these three variables now. By means of this, we can know how good our line is fitted. Okay? How much variability is explained by our regression line, and how much variability has been left out. Okay? So how much is explained and how much is unexplained. Okay? So the first term here is total sum of squares, SST, which is what it measures the total variability of the observed values around its mean. Okay, so the observed value minus its mean, this is SST. The second term in the decomposition is what? Is regression sum of squares, SSR. Okay, what it measures is the variability of the fitted value around the means, the fitted value. Okay, so in the first case we have the mean value of the fitted line. In the next we have y hat. Okay, so the predicted value minus the mean value of the regression line. Okay, and the third term is SSE, which is error sum of squares.
This is the mean of the fit.
This one?
Yeah.
Yes. Yes.
We always subtract the mean of the fitted value.
Yes.
The first time to the real values in the data set, and the second time to
The mean. Yes. So it goes like this. Just to have a visual idea what we are talking here. Okay? We still have time, right? Okay. Okay. So, what we have? Let's say we have our regression line. Okay? This is what? Our regression line for the data. Okay? And we call this value what? Y hat. Okay? This is from alpha plus beta xi. We get this line. Okay? Next, what we have, let's say we have this mean value here. Okay? So the mean of the fitted line, which is y bar. Okay? Okay? And let's say you have an observed value, which is yi. Okay? And we predicted this value to be here. Okay? Yes. Yeah.
1 second is from the
this is our yi. Okay? The observed value, this is the mean value of the regression line. Okay? And this is what? Is yi. Okay? So this now, from here to here, if you look to the equation, okay, to the formulas, okay, so yi minus this should be SST, okay, okay, the total sum of the squares, okay, which is equal to the decomposition of these two terms now, okay. So from here, what do you have here? Should go to here, and this is the error term, which is y minus y hat. This is SSE, okay. And then from here to here, this is the error term, SSR, okay. Is clear? So, the total error is equal to the sum of this term plus this term, okay? This gives us how much variability we have captured in our linear regression model and how much we have left, okay? So the left is this one, sum of residual, okay, and this is what we have captured, okay. So this is the basic idea, okay. Now we have this derivation, you can have a look. So the value it gives us r squared is what? The coefficient to determine this variability, okay. So r square is equal to SSR, the sum of the residuals divided by the total error, okay. R you can write it 1 minus sum of squares of errors divided by the sum of square, the total sum of squares, okay. So basically R squares measures the fraction of the total variability obtained by our regression line. Clear? Okay, now the range for this value is, if this is strictly positive or greater or equal to 0, this value is greater or equal to 0, okay, this sum is between 0 and 1, okay. Then we have two cases. In case if r square is 0, if r square is 0, this means that these terms, the predicted terms, are all almost equal, so the sum of the squares of the residuals are equal to 0. If this term is equal to 0, this means r square is 0. Very poor model. We didn't capture anything. Yes, because everything lies on the line. The other case is if r square is equal to 1, this means that the sum of these squares are equal to 0. Okay, if this term is equal to 0, 1 minus 0, 0, we have perfect condition, we captured all the variability. Okay, and this can be also written in this way, dividing the each term by the total number of observation, SSR divided by n, SST divided by this. Okay, so we kind of scale it up, okay, for both the predicted and observed values, okay, and this gives us the proportion of variance for the dependent variable that is explained by the fitted line. Now a crucial point here is, this r square, this we call it, it is not caused by something, but it is just a kind of association. Okay, what I mean by this, a classical example: ice cream sold and people drowned in the ocean. Okay, what you see from this statement, there is some correlation. The correlation is, but not because of these two. The correlation is from a third variable, which is what? Temperature. Okay, so in summer people eat ice cream, go to swimming. Okay, so this doesn't mean that one is causing the other. Okay, ice cream doesn't mean people drowning in the ocean. Okay, but there is a third variable which is affecting this phenomenon. Okay, so this is the meaning of r squared. There is no cause and effect. Okay, but it just gives us this association. Okay, and if we put these values into the example of supermarket, we get these values. Okay, and r square is 0.88857. This means that the model which we have built, the linear model, explained the linear variability and the relationship between the sale and price 88.9%. Okay, so this is the variability explained by our model. How we know this? By calculating r square. Okay, and 1 minus 0.88 is what left, which is not explained by our model, which is 11.11%. Okay, okay, we have seen this now. Okay, so I guess we stop here and see you tomorrow.